So I want to talk to you about a set of problems in condensed matter physics where we are interested in collective behavior. These are strongly fluctuating systems, but these condensed matter systems are neither quantum, so h bar is set to 0. And so in my trajectory through physics, I have set h bar to 0, and then I think then Sriram said it at some point, I have now also set t to 0. So if I set h bar to 0 and t to 0, then the challenge in front of us is how do we understand materials that, such as these sand dunes, which are reconfigured, restructured, their response is determined by only external driving, but their fluctuations are unusual, and the fluctuations are difficult to understand. So what I hope to show you today is a framework that we have adopted, created, polished over the last few years to try and understand these kinds of condensed matter systems. So my collaborators in this endeavor has been, it started with Max B, who is now a faculty member at Northeastern. And I'm going to talk today about, I'll give you two examples. So one phenomena that we have studied, I will talk about the work of these two people. And then I will talk about the work of Kabir, who is a really fantastic postdoc that I've had the pleasure of interacting with over the last couple of years. Any data that you see here are either experimental or numerical simulations, and they come from either Bob Berenger's group at Duke University. These are experimentalists. This is a group of numerical simulators who do fluid dynamics simulations at Citi. So I don't do any of these. We just try to construct the analytical theory of, or try to understand this data. So I'm interested in granular materials, so I'm going to give you first my what I mean by them and why they are difficult and they don't seem to fall into any of the frameworks that we are familiar with. So these are a collection of macroscopic objects, so gravity plays a role. Thermal fluctuations are completely irrelevant because if I put a pile of sand on this desk, it's not going to move around by itself. The systems that I'm interested in are all interact by purely repulsive contact interactions. So the fundamental question that one can ask is, what gives any of this any cohesion? Because there are no attractive interactions. So there is no, unless you put some stresses on the boundaries, unless you confine these systems, they don't have any zero stress well-defined state. Friction is crucial in understanding all of these problems. Like a sand pile wouldn't be a pile if there was no friction. And states are controlled by driving at the boundaries or by body forces like gravity. And if I put a pile of anything on this desk and don't do anything to it, it'll just sit there. So they're sort of non-ergodic in the extreme sense. But they fluctuate a lot from either if you ask, if I look at different parts of my system and ask what's the nature of the spatial fluctuations, or from one realization to another. So I'm going to show you just an illustration of that. And here I'm trying to illustrate a couple of things. So one is, this is a classic hourglass. You have sand flowing through it. And what this picture quickly illustrates is, it's very hard to say whether this thing is a liquid or a solid, because here it is flowing like a liquid, but when it drops here, it forms a pile. So which is very unlike any normal liquid. But the other thing that I want to illustrate is, this is how we would normally look at it. Now, there are tools that can be used to look inside this. And what this is it's the same system in some sense, but it's not sand, but sand made out of photoelastic material. So if you look at this experimentally through polarizers, you can see where the strong forces are. So this is a very characteristic property of granular solids is that the forces are distributed extremely inhomogeneously. So this is a bunch of photoelastic discs falling through here. Now they have stopped falling. It forms this classic arch. So there are grains everywhere. So it's a densely packed system, but only some of them are carrying the brunt of the weight or the stresses. So one feature that we need to address immediately is that forces and positions are not so clearly related. Again, because there is friction, it's not a conservative system. So I'll just show you this as a dramatic example of the kinds of things that we are trying to understand. This is again a video from Bob Beringer's group. And while watching it, if you can, so again, so these are the grains. So sort of the gray background is the grains. These are the forces. So if you look at the grains, you'll see that the grains move in sort of some predictable, not that exciting a way, but the forces do something much more dramatic. So the grains are moving up, as this is an intruder falling through a bed. So the grains are moving up, not highly fluctuating in some way, but the forces are highly fluctuating. So those are the challenges that we want to address. Okay, so what has been our approach to trying to understand this collective behavior is to, So I want to give you, illustrate what we've been doing through two examples. One is a phenomena of discontinuous shear thickening in suspensions, and the other is an old problem about stress transmission in static granular media. I'll see how much I can do. Okay, so our whole approach to trying to understand the mechanisms or how collective behavior arises in these systems is to say that it's not the interactions that are fundamental, but it's really the way to think about them is these systems is that they're a highly constrained system. So the collective behavior is controlled by the fact that I have a lot of constraints that these systems need to satisfy. So the imposed stresses, as I was saying, have to add up to the sum of the stresses on all over the grain. So this is a global constraint. Then there are these local constraints. And the local constraints are this local force balance satisfied for every grain because these things are in mechanical equilibrium. There's the positivity of all forces. So if I look at the normal forces, this is greater than or equal to 0. So this is an inequality constraint. So going back to the kinds of things that I did many, many years ago, it reminds me of looking at high TC and saying I have constraints to impose, right? I have a single hole, etc. But these are slightly more complicated than that. There's also local torque balance that has to be satisfied for every grain. And so I'm doing classical Newtonian mechanics, but we want to understand these systems statistically from a statistical mechanics framework. And then there's this friction law on each contact. So this is just freshman physics. Tangential force has to be less than or equal to the friction coefficient times the normal force. So these two are inequality constraints. These are equality constraints at the local level. That's a global constraint. So what I'm going to do is construct a representation, which once I have gone through it, you'll see is a familiar trick that we all play. A representation in 2 dimensions, and I'll talk only about 2D, which satisfies this constraint, and this constraint exactly. And then we'll construct a representation in which then the correlations that arise in that representation then have to be coming from these 2 constraints that are then have to be imposed on them. So these 2 constraints are not embedded in the representation itself. The representation already satisfies all 3 of these. And then these 2 constraints lead to collective effects, correlations, etc. Okay, so I'm going to try and motivate what this representation is pictorially before I give you the construction. So again, I'm going to, so if you look at this picture, it's a similar picture of photoelastic beads, and there are forces and there are grains. This is now actually a 2-dimensional assembly, so gravity is into the board. But what I'm going to try and ask you to think about is the fact that I can do two things. So first of all, this is a granular system. The granularity also poses challenges. So the granularity tells me that there are grains, these circles, and then there are voids. Now, if I didn't know anything about the forces, or if the forces could be clearly, could be uniquely constructed from the positions, then all I would have to tell you is what are the grain positions. If I had momenta, I would give you momenta. And I could give you also alternatively, I could give you the positions of the voids. So if, let's say this is void 1, this is void 2, and there's a vector connecting them in position space. No, this is frictional. This is frictional. So these forces are not necessarily normal. So the forces have tangential and normal components. So it's a force vector at each point. But instead of doing that, let's say I want to go to a completely different representation where I say grain 1 is separated from grain 2 by this contact force. Right? So I'll just draw these 2 points on my blackboard, but the vector connecting those 2 points on my blackboard is not going to be the positional vector joining this, but the force vector joining them. Now the advantage of doing that is if under certain conditions, as I'll show you here, for very small changes in position, the forces change by a lot, then this representation gives me a better microscope to looking into what's going on. So for example, I'll run this video quickly. It's just going to be shearing the system. And what you'll again see that the grains sort of deform just affinely with some small non-affine motion, which is of course there, which is needed. But if you look at the forces, they will change dramatically. Okay, so I just stopped it here. But if I let this video continue, you would see that the forces develop. But if these two voids that I had shown you at the first step of the movie didn't move very far in position, but their forces changed by a lot. So how do we do this? And we can do this representation, a unique representation, because the grains have force balance. At every grain has force balance. So I'm first going to talk about my first set of problems, the discontinuous shear thickening. I'm going to show you the representation in one way, and then I will use a slightly different way of doing that. Okay. So if you think about it, it's actually a very simple thing to do. So this is a cartoon of my particles. And this is some two-dimensional assembly of grains, big, small, different sizes. At each contact of this red particle, there is a force. This, again, as Chandan pointed out, these forces don't have to be normal. So these are force vectors. But what I know is that the forces have to add up to 0. So what I can do is I can go from this representation and then represent this red particle by this red polygon. So this red polygon is not telling me anything about where in positional space this particle is or how far this green particle is from this red particle. It's representing it by this polygon. But because I have Newton's second law, which is forces are adding up to 0, and Newton's third law, that the force applied by the red particle on the green particle is equal and opposite to the force applied by the green on the red, then the green particle has another polygon associated with it, which shares an edge. Right? So I can take such an assembly, and then I map it on to this representation. Right? So each grain here becomes a polygon here. The polygons are perfectly edge sharing. The boundary here is completely determined by the stresses that I impose on the system. So the stresses add up to, so if my stresses are very small, this box will be small. This taken from a simulation is an isotropic compression. So this is a square. If I shear it, the box will change shape. The angle between this will tell me what the shear is. So this is not a real space representation at all. It's a stress space metric. It's a force space metric, however you want to call it. So the edges here are the contact forces. each void, so let's say if I had numbered the void here 1, numbered the void here 2, this is void 1, this is void 2. So the positions of these voids in this space, I will denote by H. So we call this the height vectors. So the difference between this void and this void is the contact force that sits here. And we all have to, so, and I'll come to this a little more precisely later on. To do this rigorously, I have to take a convention and say that every time I look at the forces acting on the red particle or any particle, I go around in a counterclockwise direction. So convention is needed. So people who have worked on other constraint systems will recognize this as height maps that people do in dimer models, in 3-color models. Here, these heights are continuous variables. There was a question back there. No. No, they don't have to be. They are compressible. Yeah. Okay. So then, for the first part of what the phenomena that I want to talk to you about, I'm going to take this approach. I'll say, okay, now I can analyze patterns in this space. Say I'm shearing it, I am doing something to it. I'll analyze the patterns in this space, and there's one very simple thing we can do, so one more thing. In this space, my interactions are purely repulsive. So when a grain, 2 grains break contact, the force disappears. Here, what the corresponding thing is 2 points will come arbitrarily close to each other. But there's no one-sidedness of forces. If I want to map sort of effective interactions here, there's no one-sidedness to it. So one thing we could do is just say, okay, I have these points and the edges between them. Let's try to understand just the point pattern. By doing the usual kinds of things we do in condensed matter system, we can look at pair correlation functions, we can look at structure factors, but all in this system. So from now on in my talk, when I say structure factor, pair correlation functions, they're all constructed in this space. So let's try to, so the first phenomena that I will analyze in today's talk, using this representation, is this phenomena of discontinuous shear thickening. So I need to give you a quick overview of what that is. Oh, I wanted to show you this movie, so I should show it to you. So this is the same setup that I was showing you before. So this is looking at these grains in real space, and the force chains will develop on this. What you see here at this point is the force tile for this configuration, this tiling. And the reason you cannot see it is the stresses are extremely small. So I haven't scaled anything up. So now I'm going to just run this. Hopefully it will work. So I'm not trying to give you anything quantitative about this at this point, even though we have done some quantitative things. But this is what happens in this space, right? So just an illustration of the kinds of things that happen in this space. So the tile expanded, and also the point pattern changed. Yes. Yes.
So you are going to lose certain particles.
Correct. So this is not a conserved number of particles. Yeah.
How do you define the energy of R? And then it's really snapshot by snapshot.
Correct. Correct. Yes. So when I'll do G of H in here, in the particular system that I'll show you, fortunately it doesn't change too much. So we have grouped then snapshots by the same number of point patterns and averaged. But yes, primarily we rely on snap G of H for each configuration. Yes?
I have 2 questions. First of all, this is dissipationless? The system has no dissipation?
No, it has dissipation, right? When there's friction, there's no fluid to dissipate it in this system, but in the other one that I'll show you, there's a fluid.
But then the sum of the forces, there's force balance at each point,
on each grain.
on each grain. So where's the, how do you incorporate the dissipation then?
I'm not understanding.
So if the system heats up, say, for example, how could it heat up?
You're talking about momentum conservation, maybe. There is no momentum. Yeah. Yeah. So these are all contact forces. These are inertia less in anything that I show you.
My second question is, what about void sizes? There'll be distribution of void sizes.
Absolutely. Yeah. Yeah. I'll come back to the void size, etc., a little later. But for this representation, the sizes don't matter. There's no positional metric showing up here at all. It's just a force metric. But the topology is maintained. Like if I have a void number 1 and a void number 2, I know what those voids are here. But their representation here is not. Okay. Okay, so my first example will be trying to understand this phenomena of discontinuous shear thickening, where if I look at the stress as a function of shear rate, and these are non-Brownian dense suspensions, you see this rapid, change. And if I plotted the viscosity as a function of the strain rate, you would see that the viscosity jumps by orders of magnitude. So this is what we're going to try and understand. And it's by now been pretty well established that friction plays a strong role in this phenomena itself. So if I just turn this around, this looks like a van der Waals loop. So a question that has obviously come up in the community is, can we think of this as some kind of a phase transition? And there is a theory. So this is what I mean by this looks like a van der Waals loop, right? So if I made, this is my strain rate, this is my stress, this is my pressure, this is my volume. This looks like there's a critical packing fraction above which I start getting the knee, right? So there is a well-established, very successful van der Waals-like theory for this rheology. And what we have been trying to do is understand what I would say is the stat-meg behind van der Waals. So what's the collective behavior that gives rise to this kind of an equation of state? Okay, so the physical picture is by now, I think, pretty well established, and the community accepts this. And the physical picture has been established by this group of papers, and I will focus on sort of the picture given by Matthew Wyatt and Mike Cates, where the basic idea is the following, that if I just looked at dry grains, not a suspension, and if I looked at, or flowing grains, so viscosity as a function of packing fraction, then I know that if I had frictionless systems, then the viscosity diverges at some packing fraction or some density. If I increase the friction coefficient, then that viscosity would diverge at a lower packing fraction. So what they propose is that you can construct a model for the rheology by saying basically what's happening is that as you shear at higher rates, which also means you're increasing your shear stress, then if I had this at low shear stresses, then I have lubricated contacts between the grains. And if I increase the stress, some of these lubricated contacts get replaced by solid-on-solid frictional contacts because the particles have some roughness to them. So if that's the picture, then the rheology model is based on saying as a function of the imposed stress, the effective friction coefficient changes. So there's sort of a self-consistency loop in there saying I'm going to increase my stress. The effective friction coefficient changes, so the system will jump from this branch to that branch, so the viscosity changes. So the viscosity goes from non-frictional to frictional. So, and this whole theory then gives a very nice description of the rheology, and the phase diagram can be constructed out of that. So what I will show you is what we have been able to extract from as what's underlying that. Okay, so this is a phase diagram constructed by Jeff and Avi using this rheological model and their, so I should have put the data points here, and their numerical data. So this is stress and this is packing fraction. And then there's a line, this red line, which distinguishes a region which is known as continuous shear thickening, so no jump in the viscosity or no discontinuity in the viscosity, but a slow rise. And this region to the right of it, which has a discontinuous shear thickening. And ignore these blue lines, we will not talk about that. So this discontinuous shear thickening. So a question that Jeff came to me with is this: can this be thought of as a critical point? Right? So this is the question that we have been sort of trying to address, looking at the configurations and the ensemble of configurations but using this representation. So of course, the standard measures in real space, if I just look at positional space, don't show any diverging correlation lines. Okay, so first I'm going to just show you, I believe the next one is, yeah. So I'm just going to show you some sample, these 4 stylings that are constructed from Jeff's data at low stress, medium stress, and high stress. And what I have done again is there are tiles here, but I've taken out all the edges, so I really just want to look at what these point patterns look like. So we will be analyzing these point patterns. So here, this is a sort of a representative 1 state. You see there's some clustering. If I blew this up, you would see there are lots and lots of points close to each other. And then there are these white regions, so the points are separated by large spaces. Basically what this is saying is there are some very small forces in the system and some very large forces in the system. And what we're trying to see is there at some point where there's sort of a clear scale separation between these? And is that indicative of any of the discontinuous shear thickening? So yeah, so you do see that qualitatively there's some change in the nature of the clustering here. This is at very high stress, seems to become somewhat more uniform in the sizes of the white spaces, etc. So what do we do with this? So this is 3 representative, so again, this is all constructed from numerical fluid dynamics simulations data. So I'm just going to show you this because what I wanted to emphasize is for this discontinuous shear thickening suspension, they're truly 2 sort of different non-equilibrium steady states. So I'm shearing them at some rate. This is being sheared at some low rates or low shear stress. This is at a high shear rate at high shear stress. So let me just do this one more time. So I have an ensemble available to me. I have an ensemble of these 4 styles. And we want to understand how these behave as an ensemble. And as Walter was saying, the number of tiles in here and the number of points are not strictly conserved because I can lose. But it so happens that it actually doesn't change very much. But we should take that into account when we do our statistical averaging. Okay, so I'm going to show you quickly what we did and what we saw. And so this is so I just want to give you the snapshot of what we did, and I don't have any time to talk about the theory that we have developed, but so what I'm showing you is the structure factor of these point patterns, right, of the 4 styles, not the real grain positions of this point pattern. This is the structure factor in 2-dimensional, so S of Qx and Qy at a low stress and low packing fraction. And this is at the same stress, but at a higher packing fraction. And what you do see is a clear change in the symmetry of this, right? So here there's a large angle, there's a small angle, the lobes have different, got it. Here it has rotated, so roughly speaking, these angles are now becoming 90 degrees. And when we go here, we get stuck at this position where I recover a complete 4-fold symmetry. So we have a sort of a theory for this now that I don't have any time to discuss. But basically the point I want to make is if I did similar measurements in positional space, we don't see anything. In this space, we clearly see this change in the structure pattern. If I now go in this direction where I'm increasing the stress, setting at the same packing fraction, it's the decay of the structure factor that changes. So the length scales are changing. So roughly speaking, because I don't have much time to go into this, there are 2 length scales in the problem. And when I say length scales here, it's actually a stress scale. So there are 2 stress scales in the problem. And at this point, these 2 stress scales become equal. So so this is what we find by analyzing the structure factor. Right? So I'm just going to, so this is an example of what we can do and what we can extract. So we would claim that the underlying collective behavior has to do with the force organization and the scales that emerge there. So the small force scale and the large force scale. And roughly speaking, at one point, the large white spaces in my force tiles and this other scale become roughly equal. And then if I'm way on this side, then there's mostly large forces, very few small forces, so there's no clustering. So for people who model very ultra soft potentials where there is no real hardcore, these kinds of or in gels, these structure factors are not so if I gave you this as a structure factor for a gel, you would not be surprised. So that's the kind of theory we are now borrowing to understand the structure factor. I have 12 minutes total. Okay, now I'm going to quickly tell you something which is a different story, which is Kabir's contribution. And we've gone back to an old problem of trying to understand, and both of this is very recent. This stuff has just been written up. So we are asking the question of how stresses get transmitted in granular materials. These are pictures from Bob Berenger's group from way back. So this is a pile created under gravity, 2 dimensions. And this is when they have exerted a point force on one particle here. So this is what happens when they do that. And these 2 pictures are just subtracting the original one from this. So this is the response. So this wave-like response has been with the community as a problem that we need to understand for a very long time. So we have revisited this, and we specifically tried to address one question, which is these patterns seem to depend on how disordered the underlying contact network is. So this is the pattern that you see after ensemble averaging over many configurations, but all of which are crystalline ordered underneath. This is a little more disordered, this is a little more disordered. So so I'm going to skip this because I don't have time, and I've given you all of this already. So another way of trying to understand what I showed you as this force tile is all I have done is I have taken a contact force here in real space, and this goes back to your questions about the void shapes. So the void shapes and sizes are all very different. It's a random network. We have characterized this network now by a polygonal, equivalent polygonal network, which I don't have time to go into, but it's much nicer than having complicated void shapes. But the voids now have polygons associated with them, and so do the grains. But each force I can write as a difference between 2 fields that sit in the void. So this is what we did to represent the forces. So the question now was, if I impose a body force or an external force, which is not a contact force, can I extend this formalism to include that? Right? Then I can ask about the response. So this, you'll immediately recognize, is just a discrete realization or a discrete implementation of divergence of sigma equal to 0. These are my vector assumptions. Okay, so now what I'm saying is, suppose now I put a body force on a grain, then these don't sum up to 0, they sum up to a body force. These, by definition, sum up to 0. That's the way I have defined them. So what Kabir's brilliant brainwave was that we can now introduce another set of auxiliary fields, which will now let me incorporate the body forces. So these fields now sit on the grains. So it's sort of like having a vector and a scalar potential, an electric and a magnetic field kind of thing. But now I know what equations these fields satisfy. Right? So these sum up to the body force on that grain. These sum up to the discrete Laplacian. So phi So if this is the grain I'm interested in, phi 1 minus phi 0 plus phi 2 minus phi 0, et cetera, this is the network Laplacian. So to get the response, all I have to do is solve a network Laplacian equation. So if you tell me what the body forces are, if you tell me what the underlying network is, this is a unique solution. And if I find that the solution that I get violates some of my other constraints, then I'll have to say that the network necessarily rearranges. So we are asking about response on a fixed contact network. So basically we are saying, what is the response that's allowed if I insist that vectorial force balance and positivity of forces have to be obeyed? Okay, so that's my story for now. So now what we have done is map this onto a spectral problem, right? All I need to do is solve for the spectrum of this network Laplacian. I now have an ensemble of these network Laplacians, which is a random matrix ensemble. I know that states are generically localized in these, so then my response will also generically be localized. So I'm just going to show you two eigenvectors of a network Laplacian constructed here just for frictionless. This is the highest eigenvalue, which is a strongly localized eigenvector. This is the lowest eigenvalue, which is less localized. And using that, Kabir has just constructed what the response would be for if I impose these body forces, which are not large, they're small, we've just blown them up to show you. And you see this heterogeneity of forces. So I'm just going to end by, so this is, to me, it's appealing because this becomes a diffusion on a random network problem. We can look at random matrix ensembles, etc. So this is, again, a response of a sheared packing. So 7 minutes my total time, okay? So yeah, so let me just conclude by saying, so I'll flash this up. So this is the, for the experts, the inverse participation ratio, which tells me how localized my eigenvectors are. We have to clean this up. We have to do a lot more work on this. And this is the density of states of eigenvalues of the ensemble of Laplacians, network Laplacians for frictionless packings. And they don't look to us like anything that we are familiar with. So I'm looking forward to talking to people about this. Okay, so let me just put up my summary slide and say that this is where we are. Thank you.
The extended eigenstates that you showed, they had these bands. I mean, what are those bands?
They seem to be like plane waves, like just a cube. I don't know. I really don't know. Yeah. Sorry, Abhishek. I don't know why those bands.
So what are the nature of these random matrices that you get? I mean, what kind of random matrices are these?
Not anything that we are familiar with. So the Laplacian, where are
I'm here.
Okay. So these are just network Laplacians. So they're just adjacency matrices with the diagonals enforcing the rule that all of the rows sum up, the elements of the rows sum up to 0. But these are not, because the networks are created from force balance, the adjacency matrices have a particular structure. So they don't seem to be either Gaussian orthogonal or Gaussian unitary or any of the known Euclidean random matrices that I, in my limited knowledge, know about.
Is there a locality in this random? I mean, is like random matrices generally there is no locality, right? I mean, so I mean, is there a spatial dependence? Like, so is there a spatial structure of this random matrices?
So this is the spatial structure.
Yeah.
Oh, in the matrix itself. No, we don't see anything. We don't see anything. Yeah.
You mentioned this critical point, but you didn't show the snapshot of the static structure factor corresponding to that.
Yeah, because, okay, good point, because that's, I should have. So what, yeah, so it looks like, No, I'll just draw it. Yeah, I don't have it. So, trying to think what this, I know what the, yeah. So it's the most, okay. So this is my compressive direction. So it looks the most, okay, it's at the point where this valley becomes the least pronounced. So it becomes more like that. No, it's the point where I have two, no, so it's not a critical point. I should have said this, but the two length scales become equal. There are two length scales in the problem. No, sorry, yeah. So there are two length scales in the problem. They become equal at that point, but nothing diverges. Nothing. Most homogeneous at that point. Yeah, the distribution, there's no clumping at that point. So it becomes the most homogeneous at that point. But there's no diverging scale. Yeah.
It was rotated, right? What exactly physically that means?
It's not in real space. It's in this tiling space, right?
Just increasing density, see that
Correct.
without shearing.
At the same shear. No, it is always being sheared.
Always been.
Yeah, so if I fix the shear stress and I go across density, it's always being sheared. If I didn't have shear, I would not have this split structure factor P. No. Oh, no, yes, this is coming from shear. This is in the force tile space, you can think of this as imposing a strain. And the strain splits the structure factor piece. So when it's rotated, what it means is there's sort of, I don't have a very good understanding, that's why I'm not saying any of these things. There's sort of a dipolar term and a quadrupolar term, and they become roughly equal at this point. If I write down an effective elastic modulus, there's a dipolar contribution and a quadrupolar contribution, and they become equal when I have this. But I don't have a very deep understanding, which is why I'm not saying very much. But the best I can say is it's the most homogeneous at that point, not the critical.
Yeah, so in this shear thickening picture that you show the diagram, etc., you think of it as having constant packing fraction, your shear strain, and then you measure shear stress.
No, these are stress controlled.
Or these are stress controlled.
Yes.
But okay, so what happens with the pressure in these systems?
The pressure is fluctuating.
It does not increase.
Oh, of course it increases. But I'm saying so the shear stress at each set of states, right? The ensemble is shear stress control. At each shear stress, there's a pressure. The pressure, of course, goes up. The pressure and the shear stress in these systems are roughly, certainly at a high shear stress, my pressure is also up. As my packing fraction goes up, my pressure also goes up, right? So all of that is changing. The way it shows up in my, is that.
And nothing special close to this onset of discontinuous shear thickening?
There is. Okay, I'll quickly draw this. So the phase diagram that most people are drawing is drawn like that, right? What we can say based on our calculations is there are actually two lines that cross here. There are two order parameters in the system. And as I cross this line, one order parameter becomes non-zero. As I cross this line, I have another, and this is a coexistence of two phases with two different order parameters. From just the structure factor analysis, we can identify two. So that's what I'm saying, or you can think of two length scales. But nothing, no divergence that I can see.